Well, welcome everybody. Super excited to be here today. I'm Tyler Kenner, and I'm joined today by Dr. Elizabeth Whitaker, who is a principal research engineer at Georgia Tech Research Institute. Uh, her interest, she's going to talk more about them, is about intelligent agents and how we can use those for modeling, simulation, interactive simulations, such as those that you might use for training or learning. And so Dr. Whitaker is going to share some of what she knows about these agent-based simulations through this lens of K12 applications for social good. So we're going to do some hands-on pieces today. We're going to talk about where we might find some places to plug in these agent-based models and simulations in the K12 curriculum. But before I do all of that, Dr. Whitaker would love for you to share a little bit more about yourself and the work that you do at Georgia Tech Research Institute.
So I work, as Tyler said, at Georgia Tech Research Institute, GTRI as we call it. I've been there for 20 years, and I do artificial intelligence research, and we do a lot of work for the government, DARPA, IARPA research. They fund a lot of kind of new innovative things, and so I do a lot of case-based reasoning, episodic reasoning about past events, a lot of cognitive reasoning in the way that humans think about things, and agent-based models, intelligent agents that do smart things for people, and a group of intelligent agents that interact with each other for agent-based modeling and simulation, which is what we'll be talking about today.
Yeah, and so with that, we'll go ahead and dive right in. I know maybe the first question on a lot of people's minds, I know this was my question when we first started discussing this opportunity to present and share. What is agent-based modeling and simulation, Dr. Whitaker?
So it is modeling pieces of information by a set of agents that interact with each other. I don't know if I am too loud. I feel myself echoing. Let me see if I can make that better.
You sound okay to me. For folks, feel free to share in the chat. Of course, Dr. Whitaker and Brian, with the screen share, I can't see the chat. So if there's anything urgent, just let me know through the audio. But
I think we're good. I think I was causing my own reverberations. So we'll start out with, if we're going to build a model that's based on a bunch of agents together, what is an agent or what is an intelligent agent? So agents are persistent pieces of software. So these are software entities that don't just perform a task and go away. They stay in memory and monitor things and prepare to take on a task when it comes their way. They can communicate with other agents or humans. They monitor the environment, reason about conditions, and act to make changes to or affect the environment. They have specific knowledges about the tasks that they perform. This is in contrast to the old-time expert systems, which took on every task. Often, intelligent agents are smaller pieces of software that have a particular thing that they're good at. And often we talk about agents that can be mobile. They can move across a network and execute on a host machine. And the agents that we're talking about in our ABMS, agent-based modeling and simulation today, will not be mobile agents. They will execute on a specific server. So attributes of intelligent agents, what are intelligent agents like? They can be mobile. They have some sort of autonomy. There's not always some other controlling system that tells them what to do. They have built into them the ability to make a decision, to monitor the environment and decide what to do next. The agents that we're interested in have some kinds of intelligence or some kinds of knowledge, some kinds of skills. They have the ability to communicate with each other or to communicate with humans. Intelligent agents can be competitive. They can work against each other, as in most of you have heard of robot soccer or auction agents that are competing with each other. They're also collaborative agents that work together to solve some problem, each one with a different set of skills. We would like our agents to be trustworthy. You obviously could have agents that are not trustworthy, but if we're going to build them to do work for us, we want them to be trustworthy. To accept delegation, if we give them a task, we would like for them to do it. Agents can be personalized. You can have agents to do specific skills for you. They're social, meaning they like to work in groups, communicate with each other. Predictable, we don't want to send an agent out to perform a task and have it do something that is completely unexpected and unpredictable. We want to be able to know what it's going to do. Cost effective, we don't want to send out something to participate in an auction for example, electric power, and have it pay way more than we're expected. They need to be skilled, and they need to live within the set of constraints that we give them. So these are what we're thinking of for intelligent agents.
And so, Dr. Whitaker, just to pause for a second, as you've gone through this and hearing you, talk more about it, the one thing that comes to my mind is, I didn't learn how to do any sort of coding in K12 or in college. And so really, I learned using Scratch or block coding, maybe like some of the teachers here probably teach with, but then also as a, consequence of teaching with it, they know it also. And those really kind of like fundamental structures or concepts in coding, the idea of an if-then statement, which is true also in math and physics, right? And so to me, it's like these are just really very sophisticated agents that can do many if-then statements, or very data-driven, sophisticated if-then statements, where they're able to make those decisions and then act, right?
When it comes down to it, we're going to build it with ordinary code that you know about.
Mm-hmm. And so maybe a little bit more about how it's used. These technologies, sorry, not how it's used, but the technologies for implementation of the intelligent agents.
Yeah, so intelligent agents are a form of artificial intelligence, meaning they have specialized intelligence. Artificial intelligence does not have to have machine learning or self-improving capability, but often it does. And so this is a set of artificial intelligence technologies, any of which can be put into an intelligent agent to help it make better decisions. So machine learning, case-based reasoning is reasoning about past episodes to learn from them and make new decisions. Rule-based reasoning, Bayes networks, which have a set of connections between different nodes that tell how things propagate through a system. Decision trees, neural networks modeled after the way human brains work. Genetic algorithms have a self-improving approach where the fittest algorithm propagates and gets more weight in the next generation. Knowledge bases, so a lot of artificial intelligence is based on having domain knowledge about what you're operating on. Natural language processing, some artificial intelligence is able to interpret human language. And planning techniques, if you're going to take several steps into the future, you want to be able to have a plan. Game theory is operating against a competitor to make a decision on how things are coming out. So any of these techniques could be applied to intelligent agents.
And just to clarify, each of them has a different purpose, in terms of not just the outcome that you're trying to get to, but also the information that you're starting with.
That's exactly right.
And so why would we use intelligent agents instead of just writing a bunch of, Python code, perhaps? And maybe you can make an intelligent agent with Python.
You can.
That's a very naive statement, perhaps, but why use this approach?
So intelligent agents are built to help people navigate complexity in systems, complexity in the environment, complexity in the tasks that they're doing. Often people have too much information. They can't read it all and filter it all. So intelligent agents can help them navigate this too much information and filter it and prioritize what they need to see. If you think about a pilot who might have too much information coming at them and not know what to focus on next, this can give that pilot some priority. What's the most important thing for you to look at? The need to personalize tasks and interactions. People do things different ways. And if you can have some piece of software that helps you look at things in your personalized way, that's useful. The need to simulate complex systems with lots of interacting actors. And that's what we're going to focus on today, a simulation of a complex system with lots of interacting components. So an ABMS is agent-based modeling and simulation. So what are agents in these simulations like? So if we're going to put a bunch of pieces of software into an environment to interact with each other to see what the outcome is like, these agents are going to represent discrete individuals, and each will have a set of characteristics and its own reasoning, the way it makes decisions to govern their behaviors and decision making. So an agent in an agent-based modeling system, modeling and simulation, is situated, meaning it exists in an environment. It interacts with other agents. It has a set of protocols for interaction, what it's allowed to do and what it's expected to do. And it can recognize and reason about the traits of other agents to know how to respond to them. Agents in an ABMS are somewhat autonomous. They have their own internal decision making, and they're adaptive. They have a memory that lets them learn and adapt from experience and know what they've experienced in this environment. So in response to new knowledge, experiences, and communications from other agents.
And Betty, as you mentioned earlier, we're going to explore this idea of what it looks like to create an agent-based model and simulation with this discrete individuals, literally individuals who behave and then interact in a certain way based off of the information that's set up. And so maybe just a little bit more about modeling and simulation here before we dive into that hands-on example.
And Sandra Watts is asking, will we get to see this and make some agents? And the answer is yes. Tyler is going to guide you through a whole simulation, and we'll give you some take home, because it's hard to do a lot of it in an hour, but we'll see how much we can do. I think Tyler believes we can build it in 15 minutes. So
that's my goal. We'll see.
So agent-based modeling and simulation is an approach to modeling a system. It's based on autonomous interacting agents. They exist within an environmental context. Agents have states and behaviors, and they react to environmental stimulus, and they interact with other agents. And these states are a representation of the things they've experienced so far in their simulation. So an ABMS can consist of a set of homogeneous agents that are just alike. But in complex systems, these agents might be different. We might have agents of different kinds that interact with each other. They might have different attributes. They might have different reasoning approaches. They might have different behaviors. So you can build a simulation in any of these ways.
And so I know for the teachers on the call, if you're like me, all of this sounds very, very, very complex. And on the face of it, you might be wondering, as I wondered, how in the world would you ever engage a middle schooler, an elementary schooler, a high schooler, even ourselves perhaps, in exploring what an agent-based model or simulation might be? And so I think with that, what I'm going to do is I'm going to take this opportunity. I'm going to stop screen sharing for a second. Thank you, Dr. Whitaker, for calling out that piece that came through in the chat. What I'm going to do now is I'm going to drop in the link, and for the participants here, this is the resource folder that we're going to use and reference a few times as we go through this next activity. But I think one of the most surprising things, and maybe this is again showing what I don't know, so that might be a dangerous road to go down. But I think one of the coolest things is that this is all based off of a language that was developed for the purpose of teaching, right, Betty?
Exactly. So this language is based on the language Logo. The NetLogo is based on the language Logo, which was developed in 1967 by an MIT professor, Seymour Papert, and he is very well known for his work in teaching children about algorithms and teaching children to program. And so starting in 1967, he had these robotic turtles, which actually existed at first in the physical world, little things kind of like a Roomba that moved around the room. And you can see a picture of him right there with one of them. And these children were taught what does it mean to write an algorithm to have your turtle move forward, to move backward, to turn so many degrees to the right, so many degrees to the left. What does it mean to give it a whole set of statements to execute one after another? And so we are very lucky that so much work has been done on this before that this language exists for us now to use to teach. Well, we use it for actual modeling of complex systems, but it can also be used to teach children. So,
which I think is just it's like such a fascinating case, like use case of the language, that it occupies both ends of the spectrum in terms of how it's used. I also think that this image of this turtle, right, with and notice y'all that it's got like this pin here that can draw, and so you'll notice an allusion to that kind of at the end of the activity with a command in logo. But it's just so fascinating. That's huge compared to how big similar devices are now, and so just like the miniaturization is really interesting. But all of this again is this NetLogo platform, right, Dr. Whitaker? And so can you talk a little bit more about this platform? Of course, this platform being, teachers, the analogy might be Scratch or Tinker in terms of kind of the GUI.
And all of those are good, and this is just another opportunity to do things. So NetLogo is an agent-based modeling framework for rapid prototyping. It was developed at Northwestern University. It uses the easy-to-learn logo language, provides a GUI, graphical user interface, an easy GUI designer, so you can put widgets, buttons, slider bars, graphs into your environment, so you can see what these agents are doing and control what they do with these widgets, the buttons that tell it to start, to stop, to move different ways, developed at Northwestern, as I said. It is Java-based in a development environment, an execution environment. It is freeware, so you can download it and use it. It is closed source. You don't get to see the program itself. To me, that's not an issue. So I'm happy to use it closed source. So in NetLogo, because of its history from Logo at MIT with Papert, he called those little turtles, those little robots, turtles. And so we still call these agents in NetLogo, they're still called turtles, even though they don't look like turtles. Agents may have a breed, and that again is a legacy of the way thinking of these agents as turtles, and it allows the separation of turtles by different desired classifications. Most variables in NetLogo are globally scoped, so that once you put that variable in there, it is available, and its value is available to anything that any of the agents that are in that program. Provides for easy iteration across manipulation of lists. That's kind of an AI thing, and it may or may not be something that you worry about. Agents in NetLogo are implemented as individual turtles, and each turtle has a memory, a set of local variables. And so there's a timeline for this simulation, and everything happens in a tick of time. So every time there's a tick of time, the turtles can all be asked to execute their desired procedures. And so this is one way to kind of control the simulation over time. So our example that I built several years ago that we decided to reuse here and update it for you all is called Germs on a Playground. And it seems like this is ever a very applicable application with COVID for sure. But when I built this, they were worried about the flu, and there's always germs on the playground. So this is an example model to show how to build a simulation with NetLogo, and it represents a set of children. So each of these agents represents a child on the playground at recess. And at the beginning, there are a certain number of children that are infected with the germs and a certain number of children that aren't. And so we have colored them. So the white children, the white pictures, not white children, the white pictures represent children who are uninfected, and the red, when they touch an infected child, if they become infected, the picture turns red. So you can use whatever you want to represent these, and we have chosen to represent a happy face for the uninfected children and a red face for infected children. And I have made up the rule here as they come within a radius of 1 step from an infected child, and I think there's a typo in there. As they come within a radius of 1 step of an infected child, they transmit germs to the uninfected children. maybe not. It's worded strangely. That's my fault. So we can watch these. Oh, sorry. You want to go back?
Oh, no. So here, actually, I think, Betty, at this time, it might be a good time just to kind of let folks start to dive in, perhaps.
Absolutely. So let me say one more thing. This is not a medically correct simulation. This is a simulation that that shows that if children move within a certain space of an infected child, they become infected. So, okay.
Yeah.
Go ahead.
But I think that last bullet point is also interesting when we go through this, and I'm going to very quickly say this little piece, is that then, you know, we can think about ways that, okay, the model, this base model that we're starting with isn't the most medically correct, but what are the ways, and this is maybe, you know, where students can then plug in, and either if you're a content area teacher trying to bring in computational thinking or computer science, or if you're a computer science teacher trying to bring in, you know, what are the other teachers on my grade level teaching at this moment in time, you can bring those pieces in. Or
yeah,
the general social good, right? Yeah. Why is it good to wash your hands? Not just for yourself, but for the other people in your classroom. So what we're going to do is we're going to do this as Dr. Whitaker alluded to. My goal is 15 minutes. We'll see how that plays out. I am guilty of over planning perhaps, but what I'd love for y'all to do is 5 minutes just to initially explore. And so when I say initially explore, I have dropped a link in the chat. I believe that you should be able to access that. I'll go back and drop that link back in here in just a moment. And in there is
Tyler. We can see the link in the chat.
Perfect. In there is an activity, Germs on a Playground. It's a PDF. So go ahead and pull that down. There's also a link to NetLogo. It's going to take you directly to starting a new logo or starting a new model in NetLogo. And so those are the two things you want to kind of play with. What we're going to do for this 5 minutes is Betty and I are going to do our best to be very quiet and not disturb your exploration as you read through the activity sheet and go through some of those steps. We'll answer questions in the chat and just smile at the camera. But then once that 5 minutes is up, we're going to come back and I'm going to share my screen with the Germs on a Playground, kind of the model that Dr. Whitaker built. That way we can kind of talk a little bit more about maybe some things that we might have run into, some snags that we might anticipate students running into, and then how we could extend this, again, with that social good lens, either in the realm of epidemiology or not. And then we'll give you 5 more minutes just kind of continue to wrap your heads around it. It's a very brief introduction, right? A crash course in NetLogo here, but 5 minutes of continued exploration. But of course, as you go through, if you're stuck, you know, if you have questions, feel free to ask in the chat. We're here, but for the next 5 minutes, I'm going to set my timer in just a second. We're going to give you the opportunity to go in, of course, to that resource folder where the link is in the chat. I'll drop that in there one more time, just in case so many folks came in late and can't scroll back before they entered. But in there is the, you've got, it is Germs on a Playground activity - Constellation CS for social good. Pull that PDF down and then open that NetLogo web - new model link. And those are the two things you need for the next 5 minutes to start to explore building that model in NetLogo. And wherever you get in that 5 minutes is perfect. So I'm going to set that timer now. Dr. Whitaker and I are going to hang out and wait for your questions to come in through the chat. So if you have any, please don't hesitate to ask them. Oh, Dr. Whitaker, Brian has a good question in the chat. For the folks who are still kind of focusing on the activity, feel free to mute us. Apologies that we're interrupting you. Brian asks, do the turtles have a head and a tail? I'm assuming, like, do the turtles have a directionality component to them? Can they
Yes,
know?
they do. Yes. So a turtle can be asked to go forward or backward, and when it goes forward, I presume that's its head that goes forward. The default, so you can pick the shape of the turtle. It could be the shape of lots of different animals. The default shape is a triangle with the front point being how it goes forward and kind of the back line, straight line, or I think it might be curved the way it goes backwards. So yes, they do have a direction, a head and a tail. So that's one of the main things about, one of the first things that they teach children is teaching it to go forward so many steps or backward so many steps, to turn to the left, turn to the right. And it's a good chance to teach students about angles. It can turn to the right 30 degrees, turn to the right 90 degrees, turn to the right 180 degrees. And so all of that. Geometry is a good thing to teach with this logo. See, I see that Sandra Watts has a question. Can you please show how to do this on the screen?
Yeah, so Betty, what I'll do really quick is let me reset, or let me open a new tab
okay.
for this, because I already have yours imported in one. So let me go ahead and open a new one, and I'll walk through the first little bit. I'm going to do it kind of quietly, that way folks can leave the session unmuted, but still kind of focus on working on theirs. So I'll do kind of like a silent screen share to walk through some of these pieces.
You can tell by my background noise, I've had a chance to try this out with real children. So.
And so, Betty, our 5 minutes are up. And so I think maybe what we can briefly do, I think with your guidance, I can probably construct some of these major pieces pretty quickly. And then I think as we do them, maybe it would be useful to kind of call out not just maybe like the specifics of the logo language, although I think that might be useful, but also, you know, thinking those computer science GSE as we go from, you know, some folks are doing elements of computer science down in elementary school, but really those middle into the high school, those foundational concepts of variables and actions or commands and loops and your agents, you know, would be one. As I think about, you know, maybe it's parallel with block coding, like sprites potentially, you know, with like Scratch. You guys can tell which I'm most familiar with in block coding when I keep referencing those pieces. But so at this point, what I've done is I've created this new model. Hopefully I don't scroll around too much for y'all. And I've gone over here, I've made sure I'm in the authoring mode, right? That way I can add new code. And I've added this setup button And of course, in that setup, one of the things, Betty, is that you have to say like what command the button goes with.
That's
Am I right?
Exactly. Do you want to open that?
Yeah.
So you can see the setup command. It says commands setup, and we're gonna. That means that we need to build a procedure that's called setup, and you build that with the 2-2 setup. There's one more thing that I wanted to show. So there is a forever button. If I don't hit the forever button, it will just go one step. So this is a setup. We only want to set up once, so that we will not hit the forever button. But when we get to the go procedure, we will hit the forever button.
Got it.
Okay.
So now I'm going to click OK.
So Irene Serrano wants to know, will they have access to the PowerPoint after this session?
Yeah, I will be sure to share the slides in that resource folder. Okay. And so what I've done now, and this is in that PDF, is I've scrolled down, opened this NetLogo code drop-down window, and pasted in the code. And so I think, Betty, kind of going back to your point, right, this idea of the procedure. So we can see that to setup here, that's the procedure. And so it looks like, kind of in my layman's understanding, everything here is mapped, if you will, to that setup procedure. Am I right? All of this. That's
right. So the to setup goes from the to setup to the first end that you see. You see the word end, and that tells me that's the end of the procedure.
And now let me ask this really quick, Dr. Whitaker. Why is it that before I do the setup piece, the to setup, why am I think this is probably like one of the unique commands for logo is this breed. And so what does this mean?
So that means that I'm going to have two kinds of turtles. One will be uninfected children and one will be infected children. And this tells me right away that I'm going to have these two kinds of turtles.
Got it.
Okay.
And then it looks like when we do that setup piece, we're describing the color, shape, size, and position.
What are the first things that go on the screen before we can start moving this simulation?
And so now what I'm going to do is I'm going to go back to interactive really quick, and I'm just going to see what happens. We'll see. Oh, of course, when I've done this setup button source, nothing has, I must have a.
Okay.
Let's see what I've done wrong here. Let me make sure that's not it.
That might be it, yeah. Try.
Let me make sure. Okay.
What does it say? Setup.
Button source, nothing named setup has been defined.
I'm sorry, okay. I can't. Yes, it's a little.
Now I'm clicking very fast because I'm embarrassed that it didn't work how we anticipated.
This is always the case, guys. There's always it always takes more time to work it out.
Let's see. Setup.
Yeah. And there are no capitals. Oh, they hit recompile code. Let's try that.
Okay. It's giving me the expected error.
Hit recompile error.
Okay.
Recompile code. Did you do that?
Yeah. Let me click setup. So, oh, Betty, you know what it is? We haven't told it how many to make.
Absolutely.
Aha. All right. So this is the part where we're getting to a variable, right?
That's right.
And so one of the cool things about NetLogo is that creating these variables is, Betty mentioned, right, they're globally, they're defined at the global level. So you just create this. Oh, of course, now it refreshes. That's fantastic. But let me go here to the one that's already finished. You see here that I have these sliders. So you can go create slider. And then your global variable, because in this code, we've already shared, looks like I might be sharing the wrong screen, y'all. I apologize for that. Let me share the one that actually matters now. Let me just jump to this one. Because we have already said, that we want to create the number of turtles that is the number of uninfected children and initial infected children. Those are the two variables, and you see this, I think, on page 3 or 4, that when we're doing this piece, we want to name those pieces, because in that setup code, we've already said, okay, we need to make this many agents. So long as that global variable name lines up with the variable name that's in that code, we're good to go. And then what it will do is, let me go ahead and switch this back to interactive, is when I click setup, I'm going to change this number to infected children to 5. I'm going to change this to 100. So I'm going to have a lot of uninfected children and then a very small number of infected children. And then that's my setup. And so I create these variables again. Let me click on this to show you. If I edit these, right, this is number of uninfected children. We're working with one, right? One agent is one child. There could be 0 on the playground. There could be 100 on the playground. This is also, I think, a great place where you can stop. And one of the big challenges, I think, is getting students to recognize the connections between here's what we're telling the computer to do when we're thinking about modeling and simulations. And Betty, I encourage you to chime in here as well, though I think you might also be answering a lot of questions in the chat.
I am answering questions, yes, sorry. Sorry, I was using this to go up.
Burners all over the stove, but getting students to think about, okay, well, what's the connection here? Can we really how big is this playground? Are there really going to be 100 kids on this playground? And if not, that's where you might change that maximum. Maybe you have something weird, like students are coming in groups. And so maybe you do want your increment to be different than 1. Maybe it's like every student has to come in a pair, so that your increment's 2. You can define what the default value is, when the simulation loads, where's that slider at? And then do you want to have units attached to it to show, what you're counting with, essentially. And so these are all places, small places where, more than just teaching, okay, this is how you type the language, but more, more of the, these are the things that you can modify to make the simulation more like what you want it to model in the real world. And so that's just my small soapbox moment there. Betty, anything that I need to show here? I know we're encroaching on that third 5-minute round where I want folks to be able to have time to go back in and play around with it themselves. But I want to make sure folks kind of know how to do things and that we're not leaving anybody out in the dark.
Sure. So yeah, I think you've said that unless somebody has a question about what you've done so far, one of the things to say is that as you're building this thing and you test the partial components, there are going to be times when you get you have an error because you haven't gotten to the point where you built the variables like Tyler just saw. As long as you know what you're going to do next, don't be completely thrown off by the fact that you get a variable. Just keep going, and then at some point you're going to have to find them all and get rid of them. But yeah.
Yeah, and again, I think from that learning progression point of view, that's a great that's a great way to kind of introduce not introduce but reinforce the idea that the computer needs to know. And even if the computer is making a decision on what the knowledge is, it has to that has to come from somewhere. That command has to come from somewhere. Unlike humans, computers can rarely infer missing information, and so they need that variable to be they need to know what it is. They need a value for it.
That's right. And I like to use long descriptive variable names like you see here, but sorry, I've got a kid asking me a question. Long descriptive variable names, but there's a good chance you'll misspell one of them when you're typing them in. So you go back through and check the spelling when you have errors. So.
Mm-hmm. And so what I'm going to do really quick is I'm going to give us just a few minutes here. I'm going to change what I'm screen sharing, and I'm going to go ahead and I'm just going to screen share the actual document. That way I can talk about one thing in brief, and then I'm going to give you a couple minutes to kind of go back and play around with things again. on your own. As y'all have questions, thoughts, feel free to please drop those in the chat. More than happy to answer those as soon as I can get the piece here that I want to open. And so when you look at, I'm scrolling really kind of fast, we get down here, as Dr. Whitaker mentioned, you might get to a place where you're using this variable or using this procedure that hasn't been defined yet. So you've got to, that's the next step then obviously is to define that piece. The cool thing is that this syntax is pretty accessible, even for, students middle school who probably have had some experience before. I think, using the simulations is something that certainly would be accessible for even elementary school students, given how visual it is. But because the syntax is really easy and it's really easy to modify these things, either through the GUI or again through that simple syntax, you have all these areas in which, and this is where that social good piece comes into play. Let me zoom in so we can actually read here. Is, okay, Betty defined that radius as one step. Well, what if we have something that is more airborne, and so maybe that radius needs to change? How could you adjust the radius? And is that something that you would continue to then make that variable something that's locally defined, kind of equal to 1, or do you perhaps do another global variable and then have that be a slider? Why would you choose that to be different? And so a lot of opportunities for students to not only apply, right, to take this and apply it because it's so good at modeling these complex social pieces, but then also to talk about not just syntax and technical skills, but also that idea of why would you design something a certain way, more of that design thinking really than almost anything else. And so I see some things happening in the chat. What I'm going to do is I'm going to stop sharing the window. I'm going to give us just a couple minutes to maybe ask some questions about this. And then I think because of the sake of time, we're probably going to move on a little bit. But hopefully we haven't left anybody out too much with not knowing what we're doing or how we got there. And so, Sandra, I think for sure. So, how would you use this with middle schoolers? Some specific ideas, maybe. Let me go back to the PowerPoint because I think that's a great segue to where we're going next. Before I talk about that, it might be useful for us to hear how these are actually used in real life. What industries use these, and so for that, I'm going to toss it back to Betty of the when and where folks in the field use agent-based modeling and simulation.
So the domain, when we want to use the agent-based model is when the domain is naturally represented by agents or individuals interacting with each other. There's some types of domains or problems where agent-based model may not be the right thing, where they have discrete behaviors and decisions that you can program in for individuals. A place where the agents need to have dynamic adaptive behaviors where they're going to see something and change what they do in relation to that. They can have dynamic relationships with other agents. They can have friends, they can have cliques, they can have clubs, they can have organizations. So when the individuals might form into organizations, that's also a good time to use an agent-based model.
And so with all that in mind, there's obviously some, these complex systems of individual actors kind of emerge.
Right. So they can be used to model the stock market or model some economic system where people buy and sell things, where things become expensive, more expensive, less expensive. They can be used to model supply chains, spread of disease, as we've talked about already. There have been some interesting if you do a web search on agent-based models, there are some that model ancient civilization behaviors, and I find that to be interesting. Reactions of individuals and organizations to environmental change, policies, climate, violence. What if you tried to model agents behaving under a new policy, and you see how they interact with each other to try to go about their lives and accomplish their goals. Agent-based models have been used for electric power markets, for auctions in that world. So,
and so I think there's these obvious there's these places professionally But Dr. Whitaker, you shared these 6 questions, which I think are really useful for students that might, have now encountered maybe more than one way to approach solving a solution using computer science. And so, would you mind really quickly walking through kind of the thinking behind 6 questions, knowing that teachers, as we've got these last 14 minutes, sorry, Betty, I'll keep it really quick. These 6 questions are something that you could use, and we have a small resource for you to do this with students to start to think about this. How could you plan? How do you plan it before you actually make it?
So these are 6 questions that we use. We built a simulation several years ago that was how the flu was spread. This was, before COVID. We were talking about more ordinary diseases at that point. So there were some questions. How does the culture of a society affect the spread of the flu, affect people's desires to go get the vaccine, affect whether they stay home when they're sick, affect whether they go out into the public? So are there things about the culture of a society and the people's personalities that affect the way a disease is spread? What are the agents? Well, in our model, they were individual people. They don't have to be. They could be groups or other such things. How will we specify the agent behaviors? So we have agent attributes that are encoded as a series of causally related cultural variables. But when you're designing your agents, you have to decide each of these things. How will we specify the agent interaction? Oh, well, in our flu model, people will meet in a geographic space, and they'll come and they'll go to work, they'll go home, and they will have the opportunity to spread the disease. You notice in the germs on a playground, the disease is spread whenever 2 children come close to each other, but there's some probability. So this is a place to introduce probability and to teach children about probability, because NetLogo has a probabilistic random function, for example, that can be used, integrated there. And what is the context? Well, you're going to build on germs on a playground. The context is children on a playground. In our glue one, we had a small city. And how will they behave? Well, each person has particular ways that they make decisions and decide where they're going. And so those can be programmed in there. And these are 6 questions that I believe set the context for how you're going to design your agent-based model and simulation.
Yeah, and so with that, Betty shared these 6 questions with me, and I just thought they were a fantastic way for teachers to identify connections across K12 standards, but then also for students to, plan that context, identify that context, and figure out that connection, right? How do I design something using computers that models or parallels the real world? And so, some examples: social studies, economics, that monitoring, bartering, trade, supply, demand. Science, obviously we explored some life science ones, but even the idea that agents can be non-human actors. And so you could use agent-based modeling and simulations to explore chemistry, chemical reactions, equilibrium, the motion of particles, right? Solids behaving differently than liquids, behaving differently than gases. Back to what Betty mentioned, math, that dice roll probability. And I think all of this also, kind of coming back to the idea, especially as we're kind of, off the tail end of the last year and a half of instruction, which, hopefully will be the only time in our lives we have to go from virtual to hybrid to maybe virtual again, and then maybe face-to-face, and all those different permutations, that social good piece. How could we use agent-based modeling and simulation to really show, I think, my personal opinion, that what you do as an individual really does matter in so many different ways, whether it's epidemiology or economics or just social behavior. How you act as an individual agent can impact others, and it has a broader effect than just the effect on ourselves. And I think that that's something that this is uniquely good for computer science, which students and maybe ourselves alike also perceive as kind of a cold and inhuman perhaps field, but this is a really uniquely good way at simulating those social dynamics. So to engage you, of course, we have 10 minutes here. Like I said, I'm really guilty of over planning, but I think Betty kept me straight on this one, so we're not too far. This is the last thing we have planned. The other resource that's in that box folder is this, which is kind of planning for agent-based modeling and simulation. And so I'm going to switch over and share this document, but I encourage you to go ahead and pull that up. I'm going to talk through the really brief example. I'm going to give myself like 2 minutes, but then I would love for you to maybe go into the standards, the Georgia Standards website, or pull up your standards document, maybe that you have from your school, your pacing calendar. Maybe just maybe you know, right? You've taught the same grade level or grade level bands for years, and so you know the standards you're looking at. You don't need any help there, and so maybe that would be something that you can just have in the back of your mind. And so if I can find the piece I'm looking for here, I'll go ahead and pull it up. And then, of course, as we go through, as you have any questions, we've got 9 minutes left. So now is as good as any time to drop those questions into the chat. That way we can answer them. Hopefully we've shared a little bit. An hour goes very fast, but hopefully enough that you guys have kind of a starting place. The really nice thing also about NetLogo, and we can talk more about this, is that there's an absolute like wealth of documentation with all of the language, right? The dictionary, which we've also linked to in that quick start guide, also at the end of the activity for Germs on a Playground. So there's a lot of resources to help both you and students learn more about how to use NetLogo. But this document right here, again, this is all about that planning piece. And so, even thinking down all the way to 5th grade social studies, describing how consumers and producers interact in the U.S. economy, specifically thinking how competition, markets, and prices influence consumer behavior. So how could you use an agent-based model and simulation? And this is something that for 5th graders, yeah, maybe they aren't starting from creating a button and doing all the sliders, but there is certainly the idea that, introducing them to the idea of computational thinking. How can you have students engage in using this, maybe a finished one, right? A finished model, a finished simulation, where they can then use computational thinking as a way to answer this driving question. How do prices influence consumer behavior? I'm a former science teacher, so I'm always about inquiry. And to me, this would just be a really cool thing. Build the simulation, ask the students the question, give them the simulation, and they have to come up with the answer. And here's kind of the answer. So we've got, what is the question we're trying to answer? Well, we're trying to know how the price of an item impacts how many consumers purchase that item. Who are the agents? Here it's the buyers and sellers. There's different ways we could think about it. This is the way I thought about it. Sellers set the price of an item. Buyers have money and want the item. Buyers have a budget and know how much they want or can spend on the item, and sellers know how much they need to sell the item for in order to make a profit. When they interact, the buyers will judge whether or not the price set by the seller is worth the cost. The seller has already determined the price and does not haggle or barter. The stores are the space, right? So sellers have the prices. The buyers can go to one store or many stores. They can move around. And the buyers will purchase the item if it is within their budget. And if it's not, they'll go to another store or stop attempting to purchase the item. If many buyers want the item, the sellers may raise the price because of demand. If few buyers want the item, the sellers may lower the price because of demand. I see some things happening in the chat. I'm going to move my windows that way I can see them. This is all, again, just kind of a very brief idea. This is something I wouldn't ask my students to build, but maybe use as a way to introduce computational thinking, maybe into that core content of social studies. Also, you probably don't have to build it. It probably already exists on NetLogo Web or somewhere else. Or if you run into a grade level standard that you would love to have a NetLogo simulation for, reach out to us. We'll find some time to maybe get some folks like Betty to make a really great one and get that out to y'all, because we definitely, I personally think this is a really cool thing. And so we've got 6 minutes left. Betty asked a really great question. Has anyone built a portion of the model that they can make run? Or at the very least, has anyone built a portion of the model where you can make the smiley faces show up? And would love to hear the outcomes of that. 5 minutes left, and so certainly welcome your questions, your ideas. That last activity is just, again, to help you kind of think through what that might be in terms of looking at a standard, then mapping that into an application of that agent-based model or simulation.
So some things to try. You can right away, you could change the colors or the shapes of those agents, because that's something easy that has immediate changes. You can change the size of the step. Right now, I think each agent goes forward at every tick 0.5 steps, half a step. You can, so one of the first things to do to make it a little more realistic is to add a random variable. So that instead of if X gets close, if an agent gets close, an infected agent gets close to an uninfected agent within a radius of 1, they get infected. You could change it to roll a random number, 1, 2, or 3. If it's a 2, then they got infected. If it's a 1 or a 3, they didn't. So, and that's a really easy, if you look up in the dictionary random, you can make the random function run and put it into that. So that's another thing that I would try. One interesting thing that I was going to tell you that I couldn't figure out how to do it. And so the web NetLogo is a new thing. And I just learned about it a couple weeks ago when Tyler said we wanted to do this. So I've been running the desktop one. There is something called wrap, where if wrap is on, if the students walk out one side of the playground, they show back up on the other. If they walk out the top of the playground, they show back up on the bottom. That's not realistic. And so there is a place in the settings, environment settings, of the desktop version where you turn off wrap, so that if a student walks to the end of the playground, it's like there's a wall there and the student has to come back in. So wrap is an interesting thing you should look at, and we need to find out how to do that to stop it from wrapping on the web version of NetLogo. So the current way it's set up, wrapping is as if it's a torus, as if it's a cylinder on one side and a cylinder on the other side, so that the two edges touch each other, which a playground does not do. Any questions? What?
The one thing I wanted to share, Brian mentioned that he left that simulation and started exploring others. I think that's one thing I want to make sure that I share with the teachers, kind of alluding to the idea that there's a ton of already made and just really great things that exist for NetLogo. And so here's one I just found. I was kind of clicking around. 2 minutes left. I just want to show the red dot in the center is a pile of ants. And this model models how the ants will attract other ants to a pile of food. And so we can predict what's going to happen to these 3 piles of food over time. This actually deals a little bit more with the chemical marker, the
pheromones.
The pheromones that the ants leave behind that signal, right, that biosignaling to tell other ants where to go. But as a consequence of that, we see that macroscopic piece, right? And this is an experiment that we could run in our classroom, but we could also then make the computer equivalent of it. So you've got the ants moving around, you've got your 3 piles of food, you've got the purple nest in the middle, you've got the green and the white, and that's showing the concentration and the presence of that pheromone. And so you see that, right, where there's a lot of ants moving back and forth, you see that pheromone occurring. And so you've got all the ants on the right-hand side where they're not leaving any scent behind because there's no food over there. And so then we see these piles of food disappearing over time. And so again, this is something that's already built. And so, you know, you could probably spend an hour wrapping your head around it and figuring out, oh, okay, I could have students from the content area perspective think about computational thinking and computer science this way. And from the computer science perspective, introduce some of these ideas about coding and computer science in that learning progression through the lens of content area. And so it is officially 1:20. Betty, the one question I do want to ask that we haven't yet is, let's say I've got a student, they're super interested in agent-based modeling and simulation. What is the career field that could be for them when they graduate 12th grade and go on to college or otherwise?
Absolutely.
What can they do?
Well, you know what I would recommend? I would recommend they major in computer science and then go to graduate school in artificial intelligence. So that's my story. So
but certainly, you know, these systems are becoming more complex, and intelligent agents, I presume, are certainly not on the downline, so to speak, of their utilization. If anything, these systems becoming more sophisticated, more intelligent means that this is a skill, right? This idea, this concept in and out of itself is one that's pretty valuable to be familiar with.
Right. Absolutely.
Awesome. Well, I know I'll stick around in the room for a few minutes, but I think y'all have other sessions to go to. So thank you so much. That link will stay good. I'll make sure you have that link, that you've saved it, downloaded those files. I'll drop the slides also in that folder so you'll have them. So thank you so much, Dr. Whitaker, for your time this afternoon and all the time spent in
and thank you for putting all this together, and thanks to Brian and others who made all this work. So thank you for that.
Yeah.
And
absolutely.
Thanks for the folks who came and participated and who teach our children good stuff every day. During the pandemic year, I've learned how hard that is. So.
All right. Well, thank you again, Betty. And thank you, Brian, of course, the invitation. Thanks to Lynn and the folks at Godot and Constellations and CS for Georgia and all the teachers for being on this afternoon.
Thanks, guys.
I appreciate when I show up at sessions and I learn something. So thank you all for that. Like, I'm like, oh, this is cool. And it makes me miss being.
There are a ton of YouTube videos, lots of tutorials, and we just scratched the surface. So.
Yeah, I remember learning Logo when I was 13 or 14 years old. Right. So this is definitely.
My daughter reminded me that we had a version called Ladybug, and I used to have my children make or let my children play.
Right. Exactly. I do the same thing with mine. We're all right. No playing now. We're all going to work with these platforms, coding. All right.
Okay. So how old are your children? I have a recommendation.
So 8 so I have 4, 8, 10, 12 that I work with periodically.
Okay. So there is a board game called Robot Turtles that is built off of this. Obviously, somebody was using the logo, and it is not computerized, but it has these cards that let you build an algorithm, a set of steps that the agent, you can get it from Amazon, that the agents or turtles have to take. And I played it with my grandchildren last week. So
I'm going to look it up right now.
All right.
See, that's what I said. I like when I come and I learn something.
Exactly. And I learned something too, so that's great.
Well, thank you all very much. I enjoyed it, and it seems like a lot of folks in the chat enjoyed it as well. So, and I look forward to being able to share this recording with other teachers over the next few years.
And we can be in touch. So if you have questions, you can send them to us.
I'll definitely be in touch.
Thank you.
All right. Thank you, sir.